Welcome to the Crazy Hair Chemist. So another video in bonding. Bam! So today we're going to draw resonance structures. We're going to draw resonance structure number 1. We're going to draw the resonance structure of the nitrate ion. So this is one of those polyatomic ions that you have to have memorized previously. So nitrate is NO3 minus 1. There it is right there. Now what you're going to do is you're going to use your periodic table to derive the Lewis dot structure of nitrate. So number of valence electrons in nitrogen, 5. Number of valence electrons in oxygen, 6. There are 3 oxygens, 1 nitrogen, and then you're going to add 1 for that -1 charge there. So you get 24 electrons. You're going to divide that by 2, and now you have 12 pairs of electrons. The least electronegative element goes in the center. That is the element that is furthest from fluorine. So that would be the nitrogen. Then the oxygens go around it. Then you're going to place sigma bonds, that is a pair of electrons in between the central atom and the outside atoms, forming a sigma bond first. And then you're going to place lone pairs of electrons on the outside atoms. Then you're going to verify the octet rule for both nitrogen and oxygen. Nitrogen and oxygen are 2 elements which must have an octet because they are period 2. And they cannot exceed the octet rule, and they are not 2 of the elements which can be deficient in electrons. Okay? Alright, so I'm hoping that you have that Lewis dot structure drawn now. Okay? Here is one of the Lewis dot structures in which you could have had. Right here. Now I want to point out a couple of things here. The central nitrogen has an octet. Okay, because there are 4 bonding pairs of electrons with it, and that's a total of 8 electrons. Each of the oxygens that are singly bonded have 3 sets of lone pairs of electrons, and that would yield also 8 electrons around it. The double bonded oxygen has also 4, so it has a double bond and 2 sets of lone pairs of electrons, and therefore it also has 8, which is an octet. Okay. The other thing that we're going to add here is because this is an ion, it has a charge to it in the upper right hand corner of the formula. That's NO3 minus 1. The charge -1 is the charge. Okay. You're going to put this Lewis dot structure in brackets, not parentheses, but brackets, and that -1 charge in the upper right hand corner. Okay. Now the next key feature here for a resonance structure is maybe you drew this resonance structure, maybe you drew a different one. Okay, but the key feature here is that what you can do is you can draw another resonance structure. Okay, so what can you do? A resonance structure is a movement of the double bond in a different location. So what I want you to try to do is figure out where else can I put that double bond. I can put that double bond, either I can rotate it to the right or rotate it to the left. And then you're going to get this structure right here. I just happen to rotate it to the right from the first structure. Okay, that's 2 resonance structures of a total of 3 for the nitrate ion. Now, I'm hoping that you're going to see that you can actually draw a 3rd nitrate ion resonance structure that is equally valid. And here it is right here. So, now what you should see that all of these have octets. They all have brackets. They all have the -1 charge. Now, they are all equivalent resonance structures. Since they are equivalent, what I need to do is indicate that in my Lewis dot structure drawing for these resonance structures. And I do that by drawing this double-headed arrow in between the structures to denote that these are all equivalent structures. So what I'm going to do is I'm going to point out a molecule here. Okay, so the blue thing in the middle is a nitrogen, and these tan things here are the oxygens in this case. Normally the oxygens are red, but I just happen to use these. So in the first left-hand structure that we drew, okay, the double bond was right here, okay, on the left-hand side, and then the single bonds. Okay, so now the second structure, the middle structure, what happened is the molecule was rotated. Okay, and when it rotated, then I got the double bond on the right-hand side here like this. The third structure on the far right-hand side, then I rotated the molecule here like this. You should see that all 3 of these structures are really the same structure. It's just a rotation of that double bond. Okay, so therefore they are equivalent resonance structures. Each one is a different resonance structure, but they are all equivalent resonance structures. So it's a movement of that double bond. Some people view it as a rotation of the molecule, but it's truly a movement of that double bond from one location to another location. Okay, so it doesn't matter which structure, which Lewis dot structure you look at, but you can look at any one of the Lewis dot structures and get this information, and that is the axe-like structure. And that means that the central element is the A, the outside elements are the X's. The central element is the nitrogen, that's the A. The oxygens are the X's. So there's one A, there's always one A. And then the outside elements are the O's, which are, there are 3 of those, so that's AX3. That corresponds to a particular name of a shape. It also corresponds to 3 bonding and no non-bonding on the central element. Okay, there are non-bonding electrons, but those are not on the central element because those are on the oxygens. So this is 3 bonding and 0 non-bonding on the central element. And this corresponds to a name of a shape, and that's trigonal planar. And you should have seen that in this molecule that I had here for you. They are, all the atoms are in the same plane. So that corresponds to a bond angle of 120 degrees. And this molecule is polar. It is polar because it actually has a charge to it. That -1 charge lets you know that this is attracted to a magnetic field. However, it is not polar because the molecule is asymmetric. This molecule is symmetrical. That means that that double bond could be in any one of those 3 locations here. Okay? All right, so I'm going to point out one more thing here for you, and that is we're going to determine the bond order for the nitrate ion. So the bond order is the number of bonds divided by the number of regions. So I'm going to look at one of these structures. Any one of these structures, just like the axe-like structure, the name of the shape, and the bond angles, and the polarity can all be determined by just a single Lewis dot structure of a resonance series of structures. The bond order can be the same. And so the number of bonds around the central element, so if you look at any one of these, look at the nitrogen and look at how many bonds are around that nitrogen. I'm going to count them. 1, 2, 3, 4. So there's 4 bonds around the nitrogen. There are 2 single bonds and there is 1 double bond. Okay? But I'm just counting the number of lines, that is the number of bonds around the nitrogen. Okay, now count the number of regions where bonds are located around that central nitrogen. So the number of regions are 1, 2, and 3. Okay, I'm going to show you that on this molecule that I have here. So the number of bonds are 1, 2, 3, 4. Notice that double bond counts as 2 sets of bonds here. 1 bond, 2 bond, 3, and 4. But the number of regions is 1 region, 2 region, and 3 regions here. Okay, so the bond order is the number of bonds, which is 4, divided by the number of regions, which is 3. So we get a bond order of 4/3. Okay, so one of the key features about resonance structures is that when we draw a Lewis dot structure, we cannot draw the correct Lewis dot structure. So really, a resonance structure is kind of a fake representation of what the molecule really is. In the nitrate molecule, every single bond between the nitrogen and the oxygen is equivalent. That is, there are no single bonds and there are no double bonds in the molecule of nitrate if you were to do this experimentally. So therefore, each bond is 4/3 of a bond. They are all equivalent bonds. Drawing resonance structures is a way to denote this. Okay, and by determining the bond order, you can figure out the bond energy, the bond length of each of those bonds. Each of the bonds is 4/3 of a bond. That is 1 1/3 of a bond. So I can't draw a line to represent 1 1/3. Okay, so therefore what I have to do is I can represent single bonds, double bonds, and triple bonds with the lines, but I cannot represent any other type of bond. So I have to draw resonance structures to represent that. So just remember, in resonance structures, there are no double bonds, there are no single bonds within the rotation of those bonds. Therefore, in this particular case, each bond order, that is, each bond is a length of 1 1/3. It has the energy that corresponds to 1 1/3, which is slightly greater than 1, a single bond, and slightly less than a double bond. Okay, that is the nitrate ion. There are 3 total resonance structures for that. Again, this molecule is polar because of the charge, not because of the symmetry, because it is a symmetrical molecule. I hope you enjoyed that resonance structure and Lewis dot structure here for the nitrate ion. I am the Crazy Hat Chemist, and boy, oh boy, I have a crazy hat for you. And this is coming from Cisco Systems. That's a computer system. Crazy hat. Give me a thumbs up if you like that video. Subscribe to my YouTube channel and pass on my YouTube channel to all your friends, neighbors, family members, relatives, anyone. Please pass it on and have them subscribe too. I'll see you next time for more cool chemistry videos. Bye for now.